Hello everyone. Today I'm going to present the project entitled Evaluation of 4G and 5G Networks for IoT, Performance and Scalability in Urban Areas. The aim is to understand how 4G and 5G networks behave in a dense communication scenario, simulating a smart city and exploring the impact of using IoT devices. With the growth of the Internet of Things, or IoT, more and more devices are being connected to facilitate everything from simple tasks to large-scale automation in the cities. However, this brings challenges for communication networks. With the popularization of IoT, it is possible to see how these devices are present in your lives, from domestic devices to more complex systems in cities. The basic ideas behind IoT is the electronic device that is connected and can exchange information to optimize operations and monitoring. However, the current infrastructure, mainly based in 4G networks, faces clear limits. 4G networks, which are widely used for IoT, have problems handling the volume and the diversity of traffic limitations, higher latency, and the difficulty supporting a high number of devices connected simultaneously. These challenges make it difficult, for example, to support real-time traffic monitoring systems and manage smart traffic lights without delays. In addition, 4G cannot fully meet the requirements of machine-to-machine communication, which are essential for smart cities. As a result, 5G has emerged as a promising solution. This technology is designed to support a much larger number of devices and with a much higher data transmission speed than 4G. In addition, 5G offers extremely low latencies, enabling almost instantaneous communication between devices. In a smart city, this would be essential for critical operations and security systems. 5G also allows the network slicing to prioritize the traffic of different applications. However, the adoption of 5G is still at a early stage in many places, and there are doubts about its implementation. Despite the promises, the large-scale implementation due to inconsistent performances and coverage problems, especially in dense urban areas where the 5G infrastructure needs more antennas for adequate coverage. Many places still rely on 4G to fill these gaps, and this complexity brings high costs and challenges to integrate it with existing networks. Therefore, understanding the impact of 5G on IoT and evaluating its performance is essential, and that is what is shown with this project. Now, about the methodology research. For methodology, we decided to simulate a urban environment with two networks, a 4G network and a 5G, each connecting 100 devices with half of them simulating temperature sensors and the other half location sensors. These devices communicate in continuously with a central server. To carry out the simulation, we use network simulation or NS3, a powerful tool to allow you to adjust and measure network parameters with a high level of precision. We chose NS3/2 such a Cisco packet tracer because it is better suited to simulating networks with high density of devices and the detailed control of packet traffic. For example, NS3 allowed us to control bandwidth, latency, and jitter, simulating realistic conditions that would represent a smart city. Speaking a little about the title of the simulation. The simulation lasted 16 seconds, which we considered sufficient to observe a consistent behavior without requiring too long runtime. The 4G network is configured with bandwidth between 10 and 100 megabits per second, while 5G network is configured between 1 and 10 gigabits per second. Latency also varied. We configured 4G with 25 milliseconds and 5G with 10 milliseconds. URIM has to simulate the saturation of the 4G network and at the same time observe how the 5G network copes with heavy traffic. The results show clear difference between the two networks. In 5G, daily packets remain consistent below 100 milliseconds, while in 4G network we observed delay peaks of up to 600 milliseconds, which indicates network saturation at times of high load. With regards the jitter bot resultant showed small variations, with the 4G network showing slight more instability. The 4G network had showed packet loss, while the 5G had no packet loss, which shows its robustness in a scenario with high communications demands. The data reinforcements the 5G not only offers great bandwidth, but also great stability, which is essential for IoT systems in smart cities. The 5G networks are being proved capable of supporting a larger number of devices without compromising the quality of communication, something that was not possible with 4G under the same conditions. 5G, in conclusion, the implementation of 5G is clearly a major step towards the future of smart cities. Its ability to connect devices coupled with low latency and the high throughput solve problems that 4G networks face today. With 5G, real-time monitoring, applications such as intelligent traffic systems and even autonomous vehicles become very viable and safer. The adoption of 5G in IoT networks also brings a significant reductions in delays and greater reliability for critical applications. This type of infrastructure allows entire cities to manage more efficient, from public transporting to energy management and security. Although the implementation of 5G still faces challenges, the results obtained here reinforce its potential to become the basis for high-density smart cities in the future. It is a summary of our project to evaluate 4G and 5G networks in a urban IoT environment. The results prove the 5G technology is better equipped to deal with the needs and the growth of IT in urban environments. Thank you very much for your attention, and I'm happy to answer any questions.